We are now going to analyze an algorithm for the maximum independent set problem. And again, we are going to try and upper bound the running time as a function of the number of vertices of the input graph, so as a function of n. So in the maximum independent set problem, the input is a graph G, and the output is the largest independent set of G. So largest set of vertices, so that there's no edge in the graph that joins any of these vertices. The algorithm that I'm going to present will actually compute the size of the largest independent set, but it's easy to modify it so that it actually outputs a largest independent set. So how does the algorithm work? Well, the input is a graph G, and the output is the size of the largest independent set of this graph G. There's one halting rule. If the largest degree of the graph is at most 2, then the algorithm calls a function that returns the size of the largest independent set of G in polynomial time, and it returns the resulting value. There's a simplification rule now, namely if the graph has a vertex with degree 1, then it wants to put this degree 1 vertex into the independent set. And by this, it can then remove the degree 1 vertex and its neighbor and compute the largest size of an independent set on the remaining graph. So it returns 1 plus what we get from the recursive call on G minus the closed neighborhood of this degree 1 vertex. Next, there's a branching rule for the case where the input graph is not connected. So our graph now has at least 2 connected components. So there's 2 subgraphs G1 and G2, and there's no edge between those. Then what the algorithm does, it computes the size of the largest independent set in G1 and the size of the largest independent set in G2 and just returns the sum. Otherwise, the algorithm selects a vertex with largest degree in the graph, and it just does a select discard branching. So either it puts this vertex into the independent set. If it does that, then it deletes this vertex and all its neighbors and computes the largest independent set or the size of the largest independent set in the remaining graph. And we get a +1, of course, because we put this vertex V into the independent set. So that's one option, and the other option is we discard the vertex, which means we don't put it into the independent set, and then the size of the largest independent set is the same as the size of the largest independent set in the graph G minus V. So it selects this vertex and does a exhaustive branching on this vertex, where we either put this vertex into the independent set or not. So the correctness of this algorithm is quite obvious. Maybe we have to be a bit careful about the degree 1 rule. So why is that one correct? Well, this lemma says that if V has degree 1, then G has the largest independent set that contains V. And the proof works as follows. So if we consider some maximum independent set of G, and V happens to be inside, then we are done, because now we have found the largest independent set that contains V. If this largest independent set does not contain V, then we can ask ourselves, well, this vertex V has degree 1, and so it has one neighbor, it might have other neighbors. So since our independent set is the largest possible independent set, and it does not contain V, then it must contain the neighbor U. Because otherwise, we could just have added V to the independent set, and meaning that, well, the independent set we had was not actually a largest one. So it must contain U, but now we can just modify the independent set. We can remove U from the independent set and add V instead. So that's still a valid independent set, and it has the same size. Therefore, doing this modification gives us a largest independent set that contains V. Okay, so I think that's it for the correctness. But now, what is the running time of this algorithm in terms of the number of vertices? So in terms of n. And, well, it's not obvious actually. Because, well, we select this largest degree vertex, and we can assume it has degree at least 3. But then what happens to the neighbors of this degree 3 vertex? So if they were degree 2 vertices, they now have degree 1, and then they disappear due to a simplification rule. If they had degree 3 before, then they now have degree 2. And then we are not going to branch on those vertices anymore. So it's not so obvious, but we can give it a try.
We start with the simple analysis. So here we are going to try and upper bound the running time of an algorithm, of a branching algorithm, by, well, first of all, upper bounding the height of the search tree, and then also upper bounding the number of leaves of the search tree. So let's call our branching algorithm algorithm A. And so we have two constants, we have an alpha and c. And c is basically the degree of the polynomial that upper bounds the work the algorithm does at each node of the search tree. And alpha will be used to upper bound the number of leaves of the search tree. Okay, so let's assume that on an input I, the algorithm calls itself recursively on instances I1 to Ik. And at each node of the search tree, it uses time, order, the size of the instance to the power c. And so to upper bound the height of the search tree, we need to guarantee that we make some progress at each branching step. Right? So whenever we go from a parent to a child, we say that the instance should decrease in size. So I sub I should be smaller or equal than this, or should be strictly smaller than the size of I. And since we want to upper bound the height of the search tree by, let's say, a linear function, we require that the size of I sub I is at most the size of I minus 1. Okay. And now to upper bound the number of leaves of the search tree, we have the constraint number 2 here, which says that 2 to the alpha times the size of the first instance we create, plus dot dot dot, plus 2 to the power alpha times the size of the last instance we create for the recursive calls, should be at most 2 to the power alpha times the size of the input instance. So if these two sets of constraints hold for each branching that the algorithm does, then the algorithm solves any instance I in time, order, size of I to the power c plus 1. So that's the work it does at the nodes of the search tree, and then there's another linear factor to upper bound the height of the search tree, times 2 to the power alpha times the size of I. Okay, let's try and quickly. To prove the simple analysis lemma, we use induction on the size of I. And so the first thing we do is we replace the big O's by adding a constant factor, let's call it d. So instead of big O of the size of I to the power c, we'll say that the running time is d times the size of I to the power c. So now for the base case, assume that our instance has size 1. So what do we need to prove? Well, we need to prove that if our instance has size 1, then the running time is at most d times 1 to the power something, so that's 1, times 2 to the power alpha times 1. But since alpha is more than 0, to the power alpha is more than 1. So we get d times something that's at least 1. Okay, so that covers the base case because d is at most what we had here. Now, we use induction, so we suppose that the lemma holds for all smaller instances. So for all instances of size at most cardinality of I minus 1. And we will then prove that using our inductive hypothesis that the running time of the algorithm is also upper bounded by what we need. So let us denote the running time of the algorithm on the instance I by t sub a of I. So now what the algorithm does, it does some polynomial amount of work at this current node of the search tree, and so that's at most d times the size of I to the power c. And then it makes its recursive calls. And for the recursive calls, well, it uses time ta of I sub I for recursive call number I. Okay, so because I sub I is smaller than I by condition number 1 here, we know that we can use our inductive hypothesis. So we'll go ahead and replace all these running times ta of I sub I by, well, the corresponding expression here. Okay, we also know that I sub I has size at most I minus 1. And now we can take this out of the sum. We can also take the d out of the sum. Okay, and the next thing we do is, well, we use the second constraint here, namely that the sum of 2 to the power alpha times the ii's is at most 2 to the power alpha times the cardinality of I. So we replace this sum here by 2 to the power alpha times the size of I. And then we just do some arithmetic and combine these two and observe that the total running time is at most d to the power the size of I to the power c plus 1 times 2 to the power alpha times the size of I. And this inequality holds because alpha times the size of I is more than 0 and c is at least 0. So we get exactly what we need here. So let's continue and analyze our concrete algorithm using this lemma. So at each node of the search tree, what does the algorithm do? Well, it checks whether the maximum degree is at most 2. It checks whether there's a degree 1 vertex. It computes the connected components of the graph, and then it selects a vertex of maximum degree. All of this can be done in n squared time. Now, we will get some constraints from the branching. And so, okay, so the first thing we can observe is that does the size always decrease by at least 1? So for the simplification rule on degree 1 vertices, yes, because we delete 2 vertices. If the graph is disconnected, well, in each recursive call, we delete at least one of the connected components. And in the branching rule, we also delete either one vertex or a vertex and all its neighbors. So for every recursive call that we make, the size of the instance decreases by at least 1. So let's apply this simple analysis to our algorithm for a maximum independent set. So what does the algorithm do at each node of the search tree? So it checks whether the maximum degree is at most 2, and so it solves the problem in polynomial time. It checks whether there's a degree 1 vertex. it checks whether the graph is disconnected, and otherwise it computes a vertex of largest degree, and then it creates the sub-instances for the branching. But all of this can be done in n² time. So that's it for the running time spent at each node of the search tree. We have this constraint here that the size should decrease whenever we do a branching. Let's get back to the algorithm and see what happens. So we do a branching here, for example, but here, okay, so 2 vertices get removed, so the size clearly decreases. If the graph has multiple connected components, then also these components are smaller than the graph itself. And if we branch on a vertex with maximum degree, we either remove the vertex or the vertex and its neighborhood, so the size of the graph also decreases each time. So we satisfy these constraints, number 1. Now we need to analyze the branching. And so the first branching rule is when G is disconnected, and so G1 is one of the connected components. Let's say it has the number of vertices is S. And so if S is really tiny, we will actually view this rule as a simplification rule. So we have our graph G1 here, and G2 is here. So if the number of vertices in G1 is a very small constant, then we're going to view this as a simplification rule. This is because, well, when we do the recursive call that solves G1, if G1 has a constant number of vertices, then the algorithm needs a constant amount of time to solve G1. So instead of viewing this as a branch where we solve G1, we can just incorporate this computation into our node of the search tree. So in this node, we can view this as solving G1 first in constant time, and then making one recursive call to solve G2. So and this works because, well, the computation for G1 is really fast. We are allowed to use polynomial time in our node of the search tree, and so solving G1 takes only constant time. So we do that when G1 has a small constant number of vertices, and also if G2 has a small constant number of vertices. This is so that the analysis works out nicely. So let's look at the details. So we're going to say that if alpha times S, so S is the number of vertices of G1, if that is smaller than 1, so alpha is a constant that's more than 0, so then the number of vertices in G1, S, is smaller than 1 divided by alpha. So and then the algorithm solves G1 in constant time, and we view this as a simplification rule that makes one recursive call where it solves G2. Similar, if the number of vertices in G2 is smaller than 1 divided by alpha, then we do the same. Otherwise, we know that S is in between 1 divided by alpha and n minus 1 divided by alpha. So now we have a constraint for each value of S that is in between these bounds. And the constraint is that so 2 to the power alpha times the size of the first instance plus 2 to the power alpha times the size of the second instance is at most 2 to the power alpha times the size of I. So as the size of instance, we are here going to take just the number of vertices. So we have 2 to the alpha times S plus 2 to the alpha times n minus S is at most 2 to the power alpha times n. But since we know that alpha times S is at least 1, and also that alpha times n minus S is at least 1, this constraint is actually always satisfied. Okay. So we get a constraint from this branching, but it is actually not a real constraint because it's always satisfied, and so we can just ignore it. And so actually being able to disconnect our graph into multiple connected components is an advantage for the algorithm because it can handle these connected components independently. Okay, so when the algorithm branches now on a vertex of degree at least 3, what does it do? So it either deletes this vertex or it deletes the vertex and its neighbors. So that's what happens to the instance in the recursive calls. So we have, for every possible degree that we could encounter, so for every possible value of d between 3 and n minus 1, we have that, well, the instance where we discard the vertex v has size n minus 1, and the instance where we discard, or where we select v, so we delete v and all its neighbors, so that instance has size n minus 1 minus d. And now we have this constraint here, 2 to the power alpha times n minus 1 plus 2 to the power alpha times n minus 1 minus d is at most 2 to the power alpha times n. Okay, so what we do is now we delete all of these terms by 2 to the power alpha times n. And then we obtain the constraint 2 to the power minus alpha plus 2 to the power alpha times minus 1 minus d is at most 1. So we have this constraint for every d between 3 and n minus 1. But it turns out here that, well, d only occurs negatively here. So the tightest constraint is the one where d is equal to 3. So we can now compute the smallest alpha that satisfies these constraints. So actually just keeping the constraint for d equals 3 is sufficient because all other constraints are weaker constraints. So if the one for d equals 3 is satisfied, then the others are also satisfied. So if we compute the smallest alpha that satisfies all of these constraints, then we get a valid analysis. So we could also take an alternative way to do this is to set x equals to 2 to the power alpha, and then we compute the unique positive real roots of each of the characteristic polynomials, which is obtained directly from the constraint here. So if x is 2 to the power alpha, here we get x to the power minus 1, and here we get x to the power minus 1 minus d is equal to 1. So we take this 1 to the other side and we get a minus 1 here. So if you take the largest of these roots, then we see that for d equals 3 we get the largest warning time. So in the end we'll get the value for alpha, which is 0.4650, and 2 to the power 0.4650 is about 1.3803. So now we know that, okay, for this particular value of alpha, 0.650, actually it's more precise on this slide, 0.464959. So for this value of alpha, and so c was the degree of the polynomial that upper bounded the running time at each node of the search tree. So for these two values, all our constraints are satisfied. So if we go back to the simple analysis lemma, so all the constraints are satisfied, so we conclude that the running time of the algorithm is this. So it's order n cubed times 2 to the power 0.4650 times n. Okay, so and this is how we get this running time. So this n cubed factor here disappeared. So why is that? So this is because, well, we are rounding this value here. So we get a slightly larger exponential function, and a larger exponential function is able to absorb any polynomial function. So if we round our constant here upwards, then we can get rid of all the polynomial factors. So, okay, so we get a running time of order 1.3803 to the power n for this algorithm. Okay. Can we get a lower bound on the running time? And so this is one example where we could execute our algorithm, and we could look at what running time do we get on this example. So what would the algorithm do on this particular example? Well, the maximum degree is not at most 2. It doesn't have a degree 1 vertex. It doesn't have multiple connected components. So the algorithm would choose a largest degree vertex, branch on it, and create 2 sub-instances. So for this very regular graph, it could, for example, choose the vertex v3 to branch on. And since it doesn't specify if there's multiple choices for the largest degree vertex, which particular vertex it wants to choose, we can choose. So we can choose among all the largest degree vertices and make the algorithm branch on that one. Okay, so what happens if the algorithm branches on v3? So let's say it puts this vertex into the independent set, then it deletes v3 and all its neighbors. So which means that it deletes v3, v1, v2, v4, and v5. And so now it's left with the same kind of graph. And this kind of graph is a square of a path. So we take a path, and then we also add edges between all the vertices at distance 2 in this path. So it's now again left with a square of a path on 5 fewer vertices. So it started with n vertices. Now it's left with the same kind of graph with n minus 5 vertices, where it does the same kind of operations again. Okay, so that's why we get an n minus 5 here. Okay, but what happens if the algorithm discards v? So in the second branch, what does it do? Well, it just says, okay, v is not part of my independent set. So what happens now? So this edge here disappears, this disappears, this one and this one. And so what we have now is that v1 has become a degree 1 vertex. So the algorithm would actually add v1 to the independent set, delete v2, and then make a recursive call. And now what it has is, it has again a square of a path on n minus 3 vertices. So since we have the same kind of graph where the algorithm again proceeds in a similar way, we can say that the running time for n vertices is equal to, well, the running time for n minus 5 vertices plus the running time for n minus 3 vertices, where it always does the same kinds of decisions. So now we just need to solve this equation. So here we get x to the power 5 is equal to 1 plus x squared. So if we solve this equation, we get 1.1938. And we conclude then that the running time of the algorithm on this particular family of graphs is omega, big omega, of 1.1938 to the power n. Okay, but so now there's a big discrepancy here. So we have an upper bound of the running time of 1.3803 and a lower bound of 1.1938 to the power n. So what is the real running time of the algorithm? And it's actually a mystery. Nobody knows what the real running time of this algorithm is at the moment. But what we are going to do is we are going to work on improving this upper bound here. To obtain better upper bounds on the size of the search tree, we are going to look more in detail at search trees and branching numbers. So we denote by mu of I, we'll set this equal to alpha times the size of I. So mu is some measure of how complicated it is to solve the instance. So and here for the simple analysis we said, well, the measure of how complicated it is to solve an instance only depends on the size of the instance. So our search tree computes some children, and so those also have some size. And so for the square of a path, we had that, so the search tree looked like this. So we had n vertices at the root, and then n minus 3, and then n minus 5 at the first level, n minus 6, n minus 8, n minus 8, and n minus 10 at the second level, and so on. So now the size of the search tree really depends a lot on how much we decrease this measure mu. And so let's say we decrease it by a1 in the first branch and a2 in the second branch, etc., and ak in the kth branch. Then we will say that, well, the constraint that we get is if we divide everything by 2 to the power mu. So the branch, so what the constraint we get is that 2 to the power minus a1, etc., plus 2 to the power minus ak is at most 1. So this is the constraint that we get. So we say that the left-hand side is our branching number. And we'll denote it just by a1, comma, dot, 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 comma, ak. So these are the decreases of the size of the instance, or the decreases of the measure of the instance. And we want all of these branching numbers to be at most 1. And then our constraints are satisfied, and we can use the simple analysis lemma. So we will look at some properties of these branching numbers. So suppose we have a branching number corresponding to the vector a1 to ak, and another branching number that corresponds to the vector b1 to bk. And assume that the a's are at least as large as the b's. And so we have the same number of branches, and in each branch the a is at least as large as the corresponding b. So this means that we decrease the instance by at least as much, considering the a's as when we consider the b's. So this means that, well, the branching number that we get in the end is better for the a's than for the b's. And then there's a special case here that says, well, if we have two values a and b, well, either a is at least b or b is at least a, and that's why either a comma a is at most a comma b, or b comma b is at most a comma b. The second property is the balance property. So if we have two numbers a and b, and so our branching number is a comma b, and now so a is smaller than b, If we make the branching even more unbalanced, so we decrease the smaller one, so we decrease A by some value epsilon, and we increase B by the same value epsilon, then we get a larger branching number. So it is better for an algorithm to branch into similar size instances. Okay. So we can now start talking about measure and conquer. And in measure and conquer, so the goal is to capture more structural changes when branching into sub-instances. So far, we have only taken into account how the number of vertices or how the size of the instance changes. But now we can go more fine-grained, and we can use any potential function to do the same kind of analysis. For the algorithm MRS, we think of it as having an advantage when the degree of a vertex decreases. This is because as soon as the degree becomes 1, we can simplify it away. If the degree becomes 2, then we know that we don't need to branch on this vertex anymore. So and the closer we get to 2 or 1, the better it is somehow for the algorithm. Okay, so now instead of using the number of vertices to track the progress of the algorithm, we use some other measure of the graph. And what's a measure? Well, a measure is just a function from the set of all instances of the problem to the set of non-negative reals. So as an example, we are now going to take the following measure, which is the sum of omega I times ni. So omega I is some constant that we need to figure out, and ni is the number of vertices of degree I. And for now we are going to restrict ourselves to graphs with degree at most 5, just to make it a bit simpler. So we have 6 of these omega values from omega 0 to omega 5, and ni is the number of vertices of degree I. Okay, so now when we analyze the algorithm, we are going to look at how does the number of vertices of various degrees change. And so instead of the simple analysis lemma, now we need something slightly more powerful. And the setup is very similar. So A is the same, A is some branching algorithm, C is some constant that upper bounds the running time at the node of the search tree, and now mu and eta are 2 measures of the instances of the algorithm. So eta, so is constrained here. So eta will help us to upper bound the height of the search tree. And usually we are very relaxed and loose about the height of the search tree. As long as it's polynomial, we are happy. So eta will not usually make us any trouble. We just need that we make some progress when going from a node of the search tree to a child. So it's not necessarily the case that we always remove a vertex. Maybe we remove an edge, or maybe we attach a label to a vertex where we have made some decision, but we haven't removed this vertex yet, but we have made some progress. And we need to be able to measure this progress. And this is done using eta. So the crucial part is now mu, because that allows us to upper bound the number of leaves of the search tree. And here we have the same kind of constraint as before. So we have the sum of 2 to the power mu of the sub-instances is at most 2 to the power mu of the instance. So we have that at each node of the search tree, the running time is eta to the power c. And then in the end, we can solve any instance in time eta to the power c plus 1 times 2 to the power mu of I. Okay, this lemma can be proved in very much the same way as the simple analysis lemma. Okay, so now back to our algorithm. So we consider graphs with degree at most 5. So for this to be a valid measure, what do we need for it to be a valid measure? We need that the measure assigns a non-negative real to every instance. So the measure needs to be non-negative, so we are just going ahead and constrain that, well, these omegas here, which are sometimes written as w's, are all at least 0. So if they are all at least 0, then the measure can never become negative. Okay. So next we are going to introduce a constraint that's useful for our analysis, because so it becomes quite complicated when sometimes a simplification rule triggers and we don't know how often it triggers. It might trigger very often, right? So this degree 1 rule might propagate and trigger very often, and this means that it might decrease the degree of many vertices. And we don't want that decreasing the degree of a vertex is a bad thing. So we don't want that decreasing the degree of a vertex increases the measure. Because, so in the end we are going to write down some constraints, and then we are going to say, okay, so the measure decreases by at least this much, and if some more simplification rules happen, that can only be beneficial to us. That will never increase the measure because of this constraint that we have here. So we are going to constrain that reducing the degree of a vertex does not increase the measure. So which means that so if a vertex has degree d and gets degree d minus 1, this doesn't increase the measure. So we have if you have minus omega d plus omega d minus 1, this should be no more than 0. And this should hold for every degree that's at least 1. Okay. So now we get into what our algorithm does. So if the maximum degree is at most 2, then it returns the size of the largest independent set in polynomial time. So the only thing we need is that this procedure takes polynomial time, and that's done already. So now the next 2 lines of our algorithm are the simplification rule for degree 1 vertices. So what does the algorithm do? So it just removes a vertex and its neighbor. This vertex has degree 1 and the neighbor has some degree, we don't really know. Okay, so we need to satisfy constraint 7 here. So, okay, it creates one sub-instance, so we just have 2 to the power mu of I1 should be at most 2 to the power mu of I. The next 2 lines of the algorithm are the degree 1 simplification rule. So this is a simplification rule, but we still need to satisfy constraint 7. So we need to satisfy that 2 to the power mu of I1 is at most 2 to the power mu of I. Okay, so what is mu of I1 and what is mu of I? So mu of I is just mu of G. And so the resulting instance that we get after applying the simplification rule has one fewer degree 1 vertex, and its neighbor has also disappeared. And so its neighbor has some degree, let's say it has degree d. So on the left hand side we get 2 to the power mu of g minus omega 1 for the degree 1 vertex minus omega d for its neighbor. And So we want to be able to apply the simplification rule no matter what degree the neighbor has. So we are going ahead and we write down one constraint for each possible degree of the neighbor. So for every d between 1 and 5, we get such a constraint. So now the neighbor of v might have other neighbors. And so since we remove v and its neighbor, so these other neighbors have their degrees decreased. But we already said, well, decreasing the degree will not increase the measure. So it is okay if we don't take this into account. So we will not be worse off by not taking this into account. Okay, so now we get this constraint, and so as usual we divide everything by 2 to the power mu of g. And then in the next step we take the log base 2 on both sides, and we get the constraint minus omega 1 minus omega d is at most 0 for every possible d that's between 1 and 5. Okay, but we have already, on the previous slide, we already have that for each degree, omega d is at least 0. So here we have a negative omega 1 and a negative omega d. So, and clearly if omega 1 and omega d are at least 0, then negative omega 1 minus omega d is at most 0. So this constraint here is already satisfied by previous constraints. So we don't need, we don't even get a new constraint here. The next few lines handle the case where G is not connected. And we do this in a very similar way as before. So before we said that if alpha times the number of vertices of G1 is less than 1, then we view this as a simplification rule. And so we want to do the same thing here. So if mu of G1 is less than 1, then we want to view this as a simplification rule. So what do we need to make sure? So we need to make sure that if mu of G1 is less than 1, then we can solve the instance in polynomial time. So G1 could still have many degree 1 or 2 vertices, as long as we can exhaustively branch on the degree at least 3 vertices in polynomial time or in constant time. Then we can solve the remaining degree at most 2 vertices in polynomial time, right? So we only need that, well, each vertex that has degree at least 3 increases the measure by some constant that's more than 0. So we only need that WD is more than 0 for vertices with degree D that's at least 3. So we could write down this constraint, but this will actually be implied by other constraints as well. So we don't really need it. So we have a similar situation when the other components together are very small, and we have the symmetric case. So, and now we are left with just the situation where mu of G1 is more than 1, and mu of G minus G1 is also at least 1. So, and then we get this constraint here, which is satisfied anyway. Okay, so next we have our branching rule. So our algorithm selects a vertex with largest degree, and it either adds it to the independent set or it discards it from the graph. So when it adds the vertex to the independent set, the vertex and its neighbors disappear, and then the vertices in the second neighborhood have their degrees decreased. And we say here that at least one vertex is in the second neighborhood. So if we have maximum degree 5 graph. So if we have a vertex and it has some neighbors, and our vertex has more than 6 vertices, if our graph has at most 6 vertices, we solve this instance in constant time and we don't need to do anything else. But if it has more than 6 vertices, there must be some neighbor that's somehow in the second neighborhood, because we know that our graph is connected at this point. Okay, so and this vertex, it has its degree decreased by at least 1. Okay. So that's the only thing we're going to use. We know that there's more edges going from the first neighborhood to the second neighborhood, but we are just using this for one vertex. Okay, so this one vertex, it has degree between 2 and 5, and so its degree decreases. But we don't really know what its degree is. We only know that it's between 2 and 5, and so what we have here is we write down what the smallest decrease is what the smallest decrease of the measure is when a vertex gets its degree decreased. Okay, so that's HD. Okay, for all the other vertices, what happens? So first we have the branch where the vertex gets removed and the degrees of the neighbors decrease. So what happens to the measure? So the vertex gets removed, let's say it has degree D, and then for each neighbor, and here Pi denotes the number of neighbors of degree I. So for each of those, the degree of the vertex decreases from I to I minus 1. Okay, and that's all that happens in the measure. If the vertex and its neighbors get deleted, so what happens is that, so the vertex of degree D, so the measure decreases by omega D because we delete the degree D vertex. And now it has Pi neighbors of degree I, so and for each of those the measure decreases by omega I. And then for this vertex here in the second neighborhood, we have a further decrease in the measure, and that's it decreased by HD because of this. It decreased by at least HD. Okay, so this is the constraint we get. 2 to the power mu of G minus, and then everything we wrote down on the left-hand side when V gets deleted, and then plus 2 to the power mu of G, and then minus some things because the neighborhood of V, or the close neighborhood of V, gets deleted. And all of this should be at most 2 to the power mu of G. We divide everything by 2 to the power mu of G, and we get this constraint here. Which looks a bit complicated, but okay, that's what we get. So we get such a constraint for every possible degree D that's between 3 and 5, because V has degree at least 5, at least 3 and at most 5. And so the neighbors of V have degree between 2 and D. So no neighbor can have degree more than V, because V was selected as a maximum degree vertex. And also, so all of these Pi's together, they should sum up to be exactly D. So because V has D neighbors, and Pi denotes the number of neighbors of V of degree I. Okay, so we get this set of constraints. So if we put everything together, these are the constraints that we have in the end. And I went ahead and tried a few values, and so I came up with this. So if I set omega 0 and omega 1 equal to 0, and then the omega i's are positive for I at least 2. So these are the omegas that I got, and these will satisfy all the constraints. So they satisfy all the constraints, and what's our measure? Well, we see that the largest weight here, the largest omega, is 0.4. So that's 2 divided by 5. So we know that for every vertex we have a weight that's at most 2 divided by 5. So in total, if we have n vertices, our measure is at most 2n divided by 5. So if we have an input graph with degree at most 5, our measure is upper bounded by 2n divided by 5. So now we can use our measure and conquer lemma with c equal to 2, eta equal to n, because at least one vertex disappears for each branching and simplification rule. And so then in the end we get this running time here, which is, so the exponential factor is 2 to the power 2n divided by 5, and this is order 1.3196 to the power n. So previously, what did you have previously? Previously we had 3803 as an upper bound, and now we have 1.3196 to the power n as an upper bound. So we have improved the running time now. Or we have improved the upper bound on the running time that we were able to prove. Okay. How far can we go like this? Can we find better values for these omega weights? So this brings me to optimizing the measure. So instead of manually setting these weights, we can now solve a convex program to optimize the measure. So our objective will be to minimize the upper bound on the running time that we get. So we want to minimize the maximum weight of a vertex. And we already have our constraints, and they're all convex except for the min operator here. But instead of the min operator, we can use a standard trick in linear programming and say that HD should be at most omega I minus omega I minus 1. So HD is the benefit that we get from reducing the degree of a vertex that has degree at most d by 1. And we can just say, okay, this benefit that we get is no more than omega I minus 1 for any possible value of I that makes sense. Okay, so, and then we can use an existing convex programming solver to find optimum weights. Let's see how this would look. So AMPL stands for a mathematical programming language. And this file here just encodes our constraints. So we have so we first set some parameter, which is max d, which is the largest degree, which is an integer that's equal to 5. And then degrees is a set of integers from 0 to the maximum degree. And then for every degree, we have a weight omega, which we denote by w here. That should be at least 0. So we have already our constraint that the omegas are all at least 0. And then, well, instead of just having h, I have g and h. So g is the the benefit that we get from reducing the degree of a vertex that has degree exactly I, and h is the benefit that we get from reducing the degree of a vertex that has degree at most I. So in the end, we want to minimize the maximum weight of a vertex, and we encode this as the variable wmax. So our objective is to minimize wmax. And then just to ensure that wmax is at least as large as any omega value here, we say that wmax is at least omega d, and this constraint, we have such a constraint for every value for d in our set of degrees. And then similarly, we have our other constraints. So we have a set of I separated here the constraints that we get for vertices of degree 3, 4, and 5. Okay, so how do we solve such a program? Let me quickly show you. So let me first show you the model file here, which is exactly what we had on the slide. Let me show you what we need to execute to solve this model file. Okay, so what I do here in Ample is just I reset my environment, I reset all the options, and then I set a few options. So the first option is to choose a solver, and as solver I choose here IP-opt. So it stands for Interior Point Optimization, so that's a solver developed at IBM by Andreas Wöster and his team. It's a very powerful solver for these kinds of models, but there are other solvers that work as well. And then I declare what my model is, and so that's just I just say that this is the file that I had previously here, right? And then I tell it to solve this model, and then I display all the tight constraints, so those constraints where there's no slack. This is because sometimes when we analyze an algorithm and then we want to improve our algorithm, we should look at these tight constraints, right? Because those are those that where if we are able to improve those, then sometimes we can improve the overall running time of the algorithm. Then I print the values of the variables, and in the end I print the running time, which is 2 to the power Wmax. So let's see, let me execute Ample. Okay, and what I do is just I write include mis.run, and then semicolon. Okay, so let's see what it did. Okay, so it just tells us that it's using IP-opt as we told it to. We have 15 variables. We have 95 constraints, so we generated 95 constraints out of our description of the constraints. And then here it starts solving the model. So here it tells us what's the current value of the objective function, and then in the end what it gets is an objective function value of 0.35804, etc. So here it summarizes the result it got. So this is the objective function. The dual infeasibility just tells us that, well, this is close to 0, which means that we are very close to optimal. The constraint violation here tells us that it didn't violate any constraints, which is good for our result to be valid. And then it also tells us here again that an optimal solution has been found, which is something that we are looking for. So we want a valid solution to be found and ideally an optimal solution to be found. So these are my tight constraints. We can, for example, see that for branching on the degree 3 vertices, the worst cases are when all neighbors have degree 2 and when all neighbors have degree 3. For degree 4, the worst case is when all neighbors have degree 4, and for degree 5, the worst case is when all neighbors have degree 5. These are the values of the variables, and we see here, okay, Wmax is equal to the value of the objective function, and let's quickly check, 0.358044. Yes, and these ones are all at most as large as Wmax. Okay, so in the end we get a running time, upper bound, of 1.28168660 to the power n. So this is better than what we had before. So before we had 1.31 something. Okay, let's go back to the slides. So for Ample, there's a student version available, which allows you to solve some programs and to model some programs, but not all of them. If you have many constraints or many variables, then the student version doesn't allow you to solve it. The student version is free, but if you need to solve larger programs, this might not be so convenient. So that's why this is a way to solve this in Python. Maybe let's go directly into my Python notebook. Okay, so what I'm doing here is I'm importing Pyomo. And that's a nice package where we can run these optimization problems. So the setup is the same. So my max degree is 5. This is my set of degrees. I create a concrete model. So this is M is now my model that I'm declaring. So this is my variable. These are my variables. So we have the omegas here, then the largest omega, and then again the g and h functions. Okay, so my objective function is wmax, and I want to minimize wmax. Okay, and now I declare my constraints. So this is that wmax should be at least omega d for every possible d. And what is d? The possible values for d is all the degrees. I have these for the g notation, the h notation. Let's look at the degree 3 rule, for example. So I pass it my model p2 and p3, which was the number of neighbors of degree 2 and the number of neighbors of degree 3. And this is the constraint that we have. And now we want to add this constraint to our model for every value of p2 and p3 that makes sense. So p2 is between 0 and 3, and p3 is also between 0 and 3, and they should sum up to exactly 3. So these are all the pairs now. So I have to pass it all the pairs, p2, p3, that sum up to 3. And then, so when I declare this constraint in my model, I pass it this rule here. Okay, so the setup is very similar. Now, what I'm doing here is I want to be able to use a solver that I haven't installed on my machine, but that runs on some server. And here I'm using the Neo server. And I can use IPOpt. So although I have it on my machine here, I want to try to solve this on the server. So I tell it to solve, and then write out the results, and then I write out the running time as well. So let's see what we get. So it takes some time to send this to the server, to allocate some time on the server, and to get back the results. But the solving part itself is quite quick. Okay, so what does it tell me here? The status is okay. It found an optimal solution, which is good. And so this is the running time that we get in the end. If we want more details, we can use this. So now we see the values of the variables. We see wmax has the same value, 0.3580, etc. We see here all the constraints. So here we have the left-hand side of the constraints. So for example, for the degree 5 rule, we have that the left-hand side is almost 1. But this was also identified as a tight constraint in Ample. Okay, so in this way we can also use Python to solve these programs. Okay, so the code is a bit longer in Python, but it gives us more flexibility because we have a fully fledged programming language to write down our constraints, and I could probably have written this in a more concise way here, but I wanted to use the same general setup as in AMPL. Okay, so we now get these values here for our omega variables, and now we can again use our measure and conquer lemma with these values for the omegas, and then we get an overall running time of order 1.2817 to the power n. And these weights are optimal for our analysis. This doesn't mean that this is the true running time of the algorithm. It means that for the analysis that we did and the constraints that we wrote down, maybe we ignored some side effects that happened. Maybe we could have written down more lax constraints and not, we could have maybe have improved our analysis. But our analysis is valid, and so this is now a valid upper bound on the running time. Okay, let's talk a bit about exponential time subroutines, because what we have done so far is we have proved a running time for graphs with maximum degree at most 5. So now we want to combine our analysis with branching on vertices with degree at least 6. And we are thinking that, well, branching on a degree at least 6 vertex should be very good, because well, in one branch at least 7 vertices disappear. So and that shouldn't give us a big running time, right? So we can now take our analysis for degree 5 graphs and combine it with an analysis for branching on degree at least 6 vertices as follows. So in general, our algorithm would run and branch on degree at least 6 vertices. If it encounters a graph with maximum degree at most 5, then well, it could run a subroutine where it solves the degree at most 5 graphs. All right. So now we have 2 branching algorithms. So we have one branching algorithm A and another branching algorithm B. So, and the way this works is that so we will analyze, so we'll upper bound the running time of A. And sometimes A, instead of branching itself, it invokes B. So it hands off the instance to B and tells B to solve it. Okay, so, and we assume that, okay, B has running time eta I to the power c plus 1 times 2 to the power mu prime of I. So basically mu prime is the running time for B, or is the measure that we use in the running time analysis of B, and mu is the measure that we use in the running time analysis for A. Okay, so now what do you have as constraints? So c is at least 0, we have mu prime, and eta are all measures. We have, so this is very important, so we have that mu prime is at most mu for every instance I. And now when A gets an instance, it either branches and, well, it satisfies these constraints here, or it invokes B, and we assume that, so we have already upper bounded the running time of B, and this is at most, so the exponential part is 2 to the power mu prime of I. Okay, so if this constraint here holds that if mu prime is at most mu, then in the end we can upper bound the running time by 2 to the power mu of I. The proof is not very complicated, it's similar as what we have seen before. But now what we can do is, so we can now design an algorithm for maximum independent set that works for general graphs. Okay, so our algorithm A gets as input an arbitrary graph, and algorithm B is our subroutine for degree at most 5 graphs. Okay, but now we can actually take the same algorithm for A and B, because our algorithm never said that you can't branch on degree 6 vertices. So we'll actually use the same algorithm, but a slightly different analysis. So for the analysis for A, we say that mu of g is this. So basically, every vertex gets the same weight. And the weight that we assign now to every vertex is what our previous W max was. Okay, and for mu prime, well, we have the analysis that we already did. Eta is n. So now we have that for every instance g, mu prime is at most mu of g. Because, well, every one of these w's, of these omegas, is at most 0.35805. Okay, and now what do we have for the analysis for A? So now we just need to handle branching on degree at least 6 vertices. So if we just remove the vertex, what happens is that, well, we decrease the measure by 0.35805. And if we remove all the neighbors and the vertex itself, so the number of vertices decreases by d plus 1. So we need that for every d that's at least 6, this branching number here is at most 1. And this actually holds. So one can verify that 2 to the power minus 0.35805 plus 2 to the power minus d plus 1 times this weight is at most 1. So and therefore algorithm MIS has running time 1.2817 to the power n for graphs with arbitrary degrees. So we have gotten rid of our degree constraint now. Okay. We'll talk briefly about structures that arise rarely. So remember when we analyzed the algorithm, we said that some of the worst cases are when we have a degree 5 vertex with all neighbors of degree 5. Or when we have degree 4 vertex with all neighbors of degree 4, or degree 3 with all neighbors of degree either 2 or 3. So we could try and avoid branching into these situations as long as we can. So sometimes we can't avoid it. Sometimes we have to branch on the degree 5 vertex with all neighbors of degree 5. So we choose a maximum degree vertex, and now preferably we choose one that has neighbors with smaller degree, let's say. But sometimes we can't avoid this. Sometimes we have to, the only possible choice is to select a degree 5 vertex with all neighbors of degree 5. Okay. But I'm claiming for now that we don't have to do this very often. Okay, so what's a rare configuration? So we're saying that branching on a local configuration C does not influence the overall running time if C is only selected a constant number of times when we look at a path from the root to a leaf of the search tree. Okay, so let's think about when do we have to branch on the degree 5 vertex with all neighbors of degree 5. Okay, so our graph could be 5 regular. So it could be that every vertex in the graph has degree 5. This is possible. So what do we do then? So we branch, we delete this vertex, or we delete the vertex and its neighbors. But now what happens? Suppose our graph was connected and we have branched on the degree 5 vertex, so we have taken the degree 5 regular connected graph, and now some vertices have disappeared. Which means that what we are left with is not 5 regular anymore. So we have removed some vertices from the graph, which means that if we look at what remains, it was somehow connected to what we removed. So there's some edges going from what's left to the thing we have removed. So that's why what's left is not 5 regular anymore. Even if the graph decomposes into several connected components, we still have removed something in the neighborhood of these connected components. And so even connected components cannot become 5 regular anymore. So if you take a 5 regular graph, you remove some vertices, you will not have a 5 regular graph anymore. So this actually happens only once. So when we look at the search tree and go from the root to a leaf of the search tree, we will encounter this 5 regular case at most once. And I claim that, well, this does not influence the running time. So we can actually disregard this case from our analysis. And we can prove this formally by the following, in the following way. So instead of having our measure mu, we now have measure mu prime, which is either mu or mu plus some constant c. So we add this constant c if it's still possible to encounter this 5 regular case. So if it is still possible to encounter this case, so if, let's say, our graph has a 5 regular subgraph, or like the maximum degree is still at least 6, then we say that we might encounter this case in the future. So then we add this artificial constant c to our measure. So what happened now? So the upper bound on our measure is now mu of I plus c. Okay, so in the end, if we have a valid analysis, then the running time we get in the end is 2 to the power mu prime of I, which is at most 2 to the power mu of I plus c. And this c is just a constant. So it will just add a constant factor to our running time, which will disappear in the big O notation. Okay, but what's the benefit from doing this? Well, the benefit from doing this is that if we now have this 5 regular case, so our measure still has is still mu of I plus c. So let's say we branch in this 5 regular case, right? So we create 2 sub-instances, and here the measure is mu of I1 and mu of I2. And I don't have the plus c anymore, right? Because so I've taken a 5 regular instance and I've deleted some vertices, so I don't have this artificial additional constant anymore. So I'm left with just mu I1 and mu I2 for the sub-instances. So this means that my measure has decreased by some constant that I can choose. I can choose what this constant is, and I can make this constant as large as I want. If I'm willing to sacrifice a large constant factor here in the running time, I can make this constant as large as I want. Okay, but this means that I can make my branching number as small as I want for this particular case. Because I can decrease the measure of the instances as much as I want. Okay, but this only works because, well, this local configuration occurs, well, at most once in this case, or at most a constant number of times. If some local configuration can occur a constant number of times, I might need to add a constant number of those constants. Okay, So to make use of this, I will now modify my algorithm. Instead of just selecting a vertex with largest degree for my branching, I'll choose V such that V has largest degree, and among all vertices that have largest degree, I prefer to select a vertex V that has a neighbor of smallest degree, let's say. So in that way, I avoid this 5 regular case, and also the 4 regular case, and the 3 regular case as long as possible. Okay, I still branch into 2 subcases, so I still do this select discard branch. But my new measure is now mu prime, which is mu of g plus, and then I have a sum here, and so these are these artificial constants that I add. So if g still has a 3 regular subgraph, I add this constant c3. If g has still a 4 regular subgraph, I add this constant c4. And if g has still a 5 regular subgraph, then I add a constant c5. So this in brackets I have this is an Iverson bracket, and it evaluates to 1 if the condition between the brackets is true, and it evaluates to 0 otherwise. Okay, and so I don't even need to specify what these constants are. They are some large constants, and in this way, what we can do now is I get rid of some of my constraints. So now I can say that, okay, my vertex V has degree D. I added this. So the number of vertices of degree D is not equal to D. So I restricted my constraints, so I removed some constraints from my program here. So I now just get the branching numbers when PD is not equal to D. Okay, now I can solve my program again, and so all these branching numbers are almost 1 with the following optimal set of weights. And so for this set of weights, I get a running time of order 1.2728 to the power n. We still have a big discrepancy between the lower bound and the upper bound. So the lower bound was 1.1938 to the power n. And now we have a new improved upper bound. But still, we are not exactly sure where the exact running time of the algorithm lies. Okay, and so you can read more about this topic in the book by Fomin and Kratch, and also in my book, Chapter 2, Branching Algorithms. And these are the references.